All right, ladies and gentlemen, so today's chemistry class. Let's go over some of the concepts that were discussed in class today. I'm going to begin sharing my whiteboard here. And what we're going to do is we're going to continue to discuss electron configuration. Now, so what I'm going to do is remove some of these little bars so that we can have some space. And then I can just move this over here and we can start working or reviewing some of these concepts. So today we're going to talk about the electron configuration for mainly third and fourth period elements. And we're going to review a little bit of the Aufbau Principle. And also we are going to talk a little bit about elements in the fourth period, okay? So let's go ahead. It says, according to the Aufbau Principle, after the 1s orbital is filled, the next electron occupies the s sublevel in the second main sublevel. So let me explain what that means. And basically what that means is if I have an element, an electron, that has 1s and the 1s orbital is filled up. Remember that the electrons are represented, if we use orbital notation, by the arrows, and that they have to have opposite spins. So if this energy level is occupied, that means that the electrons now have to go to the 2s orbital. That's what the Aufbau principle is stating. And what I'm going to do in a minute is I'm going to illustrate a little bit of some of the orders for this. So it says, thus, lithium has a configuration of 1s2 and 2s1. The electron occupying the 2s level of lithium atom is the atom's highest outermost energy level. So let's talk about lithium. Let's say that this is the orbital notation for lithium. Lithium, which has a chemical symbol of Li, has an electron configuration of 1s2 and 2s1. Now, what that means is, 2s1. Now, what that means is that lithium has a there's only one electron, in the 2s orbital. Okay, so that's what that means. It says, thus, the lithium has a configuration of 1s2, 2s1. The electron occupying the 2s of a lithium atom. So this electron here, the 2s1, this is what we call the outermost electron, because lithium has 3 electrons, and the electron that's in the highest occupied sublevel is what we call the outermost electron, or the highest atom's highest or outermost electron. Okay, so we'll call this the outermost electron. Okay. It goes on to say that the highest occupied level is the electron containing the main energy level with the highest principal quantum number. So going back to this, and let me delete that and write it better. So we already established that in the case of lithium, the outermost energy level is this one right here, and we say that it's the outermost energy level, and it has a number of 1. So what that means is that because the 1 electron is in the 2 in the second orbital, we say that the highest quantum number in this case is n equals 2, because the electron of lithium is in the 2s orbital. Okay, it says the inner and then the 1s2 is actually what we would call the inner shell electron. It says the inner shell electrons are electrons that are not in the highest occupied level. According to the Aufbau principle, the next electron must pair with another electron in orbital 2p rather than the third main energy level. So let me explain that real quick with some or by making reference to one of the images in your textbooks, into one of the figures in your textbooks. So first of all, the outermost energy level is in that energy level that has the final electron. In the case of lithium, that has an electron configuration of 1s2 and 2s1, this one, which is a superscript that represents the number of electrons in the orbital, is the outermost electron because it's the electron in the highest possible quantum number, which in this case would be 2. And the 1s2, these electrons, what we call the inner shell electrons, because they are the electrons that are not in the highest possible occupied level. Now, let me real quick show you guys or go over figure 3.1. And in figure 3.1, we have an order of how the electrons are paired. And what I'm going to do is I'm going to show you that, so that way when we start talking about the electrons of the third period and the Pauli principle, you guys have an idea. So basically, the electron configuration goes from 1s, assuming, of course, that electron, that orbital is filled up, they'll go to the 2s. Now, what we're going to read, according to the Aufbau Principle, the next electron must pair with another electron in one of the 2p orbitals. So we know that 1s orbital has one, or the 1s energy level has one sublevel. And then what this is saying is that instead of going 1s, 2s, 3s, it actually goes 1s, 2p, and the p orbital has 3 sublevels, which we know are represented with the lines if we're talking about the orbital notation. So after the 2p sublevel or orbitals are full, then it'll go to the 3s, and these are what we call elements of the third period, because elements of the third period are the elements that begin to occupy those 3s. And again, we go 3s. After the 3s orbital is full, we go to the 3p. So 3p. And instead of going, and then after the 3p orbital is, so elements of the third period basically go from 3s to 3p. Okay, so we call elements of the third period, or third period elements. Let me write that here. So third period elements are elements who have electrons in the 3s and 3p orbitals. So elements of the third period are those. Now, once we have the 3s occupied, then we go to the 4s. So we start at the fourth period. And elements, of course, of the fourth period are the elements who fill up the 4s. Now, orbital 3 actually has, and I forgot to mention it, 3s, 3p, and 3d. So I forgot. Let me write that down here. So elements of the third period are elements that fill up the orbital levels. And when the n equals 3, they have 3s, 3p, and 3d. But the order in which it goes is, once it fills the 3p, instead of going 3s, 3p, 3d, 4s, it actually goes 3p, 3s, 4d, 4s, and then 3d, excuse me. Now, why is that? Because remember that elements go from a lower energy level to a higher one. And the d orbitals have actually 5 sublevels, so they can hold up to 10 electrons. And because the principle states that they have to go from a lower energy level to a higher energy level, that's why once the 3p orbitals are full, they'll go up to 4s, and then they'll continue to 3d. And if you look at figure 3.5, 3d, 4p, 4s, and then so on and so forth, right? Now, when we do orbital notations, we're not necessarily going to see these very large numbers. And that's actually going to bring us to the noble gas configurations, which we're going to see in a minute. So, as I was saying, elements of the fourth period. So whenever we have elements in the third or fourth period, we start using noble gas configuration, which refers to an outer main energy level occupied in most cases by 8 electrons. So we're going to go back to this in a minute. But before we go back to that, let's talk about the elements of the fourth period. So elements in the fourth period are elements that fill up the 4s energy levels. So in third period are elements that fill up the 3s, and fourth period are elements that fill up the fourth s. Okay. So let's talk a little bit about that. I'm actually going to read from your textbooks real quick. It says um, elements of the third period. Just to review that, after the outermost octet is filled, the next in neon, the next electron enters the s sublevel, n equals 3 main energy. Thus, atoms of sodium have the electron configuration of 1s2, 2s2, 2p6, and 3s1. Okay, so elements that have that 3s orbitals are third period elements. Let me write that down. Elements that fill the 3s sublevel are elements of the third period, and elements that fill up the fourth s levels are elements of the fourth period. Okay, so before I go to noble gas notation, and noble gas notation is used in a way to simplify um, to simplify the configuration of elements that are in the third and fourth period. So let's talk about the electron notation, or the noble gases. First of all, noble gases are basically elements that are to the right of the periodic table, and they include neon, argon, krypton, xenon, and radon. And not only are they noble gases, but they are also the most stable um, elements in the periodic table. They're very stable. And the reason why they're very stable is because they fill what is called an octet. And an octet is basically when they have 8 electrons in their outermost energy level. Okay. So an octet is when they have electrons in their 8 electrons in their outermost energy level. Okay. Octets have 8 electrons in the outermost energy level. And the noble gases include neon, xenon, argon, and so on and so forth. Now, speaking of neon, when we start working with elements of the third period, again, we said that elements of the third period are elements that fill in that 3s orbital. Okay. And it's when we get to that third period, it starts to become a little bit tricky, especially because from 3p I go to 4s, and then from 4s I have to go to 3d. So to avoid that, one way that scientists or chemists have learned to work with that is by using by using noble gas configuration, which refers to an outermost main energy level occupied in most cases by 8 electrons. Okay. It says elements in the fourth period are elements that fill up the 4s energy level. Elements in the third period are elements that fill up the 3s energy level. So if we look at neon, which is a noble gas, has a configuration, an electron configuration of 1s1 or 1s2, excuse me, of 8 electrons. 1s2, 2s2, which would be 4, and 2p6, which is actually 10 electrons. So neon has 10 electrons. Now, when we start working with elements of the third period, instead of writing 1s2, 2s2, 2p6, we use a noble gas configuration. Now, for example, we have sodium. Now, sodium has the following electron configuration. Give me 1 second, guys. Sodium has an... I'm looking for sodium here. Excuse me for a minute. Let me look for that real quick for you guys. I thought I had it here. I apologize for the delay. Yeah, give me 1 sec, guys. Let me look for the electron configuration of sodium for you guys. I thought I had it here. Again, this is live and errors do happen, and they happen frequently sometimes, but that's all right. We'll get it. Here we go. So sodium has an electron configuration of, or has 11 electrons. So sodium has 11 electrons, okay? Now, if we were going to do the electron configuration for sodium, we would say 1s2, 2s2, 2p6, and that would be 10 electrons. But because sodium has 11 electrons, we have 3, we say 3s1. So there are the 11 electrons filled. Now, when we have noble gas notation, because neon, if you notice, neon's electron configuration, 1s2, 2s2, 2p6, is the same as sodium. It's just that sodium is a third period element, so that means that it has to occupy one electron has to occupy the 3s orbit or energy level. So what we do is, instead of writing this, basically what noble gas configuration is, I'll say, let's say I want the electron configuration for sodium. So what I'll do is, instead of writing 1s2, 2s2, 2p6, 3s1, especially when we start working with those third and fourth period elements, which can be quite confusing, what we'll do is we'll look for the noble gas that has the similar electron configuration. In this case, it's neon, because neon has 10 electrons and sodium has 11. So that means, instead of doing 1s2, 2s2, and 2p6, I'll say sodium, and then I'll write in a bracket, I'll write neon. I'll write neon right here, neon. And I will write 3s1. Why did I do that? Because instead of, I know that neon has the same, has the configuration of neon is similar to the first, to the configuration of sodium, at least in the first three energy levels, 1s2, 2s2, and 2p6. And all I'm missing is the 3s1. So instead of writing 1s2, 2s2, 2p6, 3s1, all I do is I simply say, well, neon is the closest noble gas to that, and then 3s1. So that's when we have orbital notation, or excuse me, noble gas configuration for neon. For sodium. Now the same is true when we start working with the elements of the third period. The same is true when we start working with elements of the fourth period. So for example, it says, and again, I'm going to read from your book. There's notice that the first 10 electrons in a sodium atom have the same configuration as neon. So the first 10 electrons of sodium and the first 10 electrons of neon are one and the same, so that's why we say neon. Now, when we have elements of the fourth period, and those are the ones that we're